Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about Y+ and wall shear treatment for laminar flows. So just to start with an overview of what I'm going to talk about today, I'm going to start by talking about how is the wall shear stress and wall heat transfer calculated for globally laminar flows. I'm then going to move on to look at how is the wall shear stress calculated for globally turbulent flows, and then I'm going to finish off by looking at how is the wall shear stress calculated when the flow is locally laminar in a small region of our domain. So just to start things off, generally, how is the wall shear stress and the wall heat transfer calculated? Now, if we start with equation 1, we see that the wall shear stress tau is given by the product of the kinematic viscosity nu and the velocity gradient at the wall. In a similar fashion, the wall heat transfer Q is calculated by the thermal diffusivity alpha multiplied by the gradient of the temperature at the wall. Now, if we think about how our velocity and temperature profiles vary in a general flow scenario, as we see in the diagram, we remember that the velocity profile near the wall is non-linear, and so of course that means that its gradient is varying in space, and so in order to calculate the wall shear stress, we take the velocity gradient at the wall, which is given by the red dotted line in the diagram there. And the same occurs for the wall heat transfer, where we take in the gradient of the temperature at the wall. And these are fundamental equations that allow us to calculate the wall shear stress and the wall heat transfer in any flow scenario if we know the velocity and temperature profiles. So what do we do in a CFD code? Now, in a finite volume CFD code, it's important to remember that the variation of velocity and the variation of temperature across cells is always linear. So that means if we have a velocity at a cell centroid, then the variation in that velocity between the cell centroid and the wall is going to be linear. And what that means is that if we look at equation 2, then the velocity gradient between the cell centroid P and the wall is going to be given by UP divided by YP, where UP is the value of the velocity at the cell centroid and YP is the distance of that cell centroid from the wall, where of course we have the no slip condition, so the velocity at the wall is 0. Now, if we remember back to the previous slide, remember that the velocity profile and the temperature profile may be non-linear. And so what that means is that if we want to calculate the wall shear stress and the wall heat transfer correctly, we need to ensure that the product of the kinematic viscosity and the velocity gradient is correct, so that we get the correct wall shear stress. And in practice, what this means is that because our velocity gradient may be wrong, then we modify the wall kinematic viscosity, that's nu with a subscript W, to ensure that the product gives us the correct wall shear stress. And if you've seen my previous videos on Y+ and wall treatment, you'll be quite familiar with this concept by now. And if not, you can always go back and check out those videos after you finish watching this one. So what I'm going to start with today is talking about globally laminar flow. And a globally laminar flow is where we set up our CFD simulation and we don't solve any equations for turbulence. So that means K, epsilon, omega, or whatever turbulence quantity we choose, we're not solving turbulence equations for those quantities. And that means that globally, throughout the entire domain, the flow is considered laminar. Now, how is the wall shear stress calculated in this scenario? So if we remember back to equation 3, we're going to want a kinematic viscosity multiplied by a velocity gradient, and that's going to give us the wall shear stress. So what we're going to do first is look at the analytical solution and use that to help us derive what form we should be using in our CFD code. Now, if we think back to fundamental fluid mechanics courses or your favorite fluid mechanics textbook, you may remember the flow scenario where we have flow between two parallel plates. And the top plate is moving, that's the red plate you can see there in the diagram at a velocity v, and the bottom plate is stationary. And the solution to this problem, the velocity profile, which satisfies the Navier-Stokes equations, is given there in equation 4. And what this velocity profile of course means is that the fluid velocity at the bottom will be 0, and the fluid velocity at the top in contact with the moving plate will be given by capital V there. And so for this flow scenario, as we know the velocity profile, we can calculate the wall shear stress. And the way we do that is by differentiating the velocity profile, which you can see there in equation 5, and then multiplying by the kinematic viscosity of the fluid, and that gives us the result there in equation 5, that the wall shear stress is given by the kinematic viscosity multiplied by the velocity of the plate V divided by h, which is the thickness of the fluid layer. So how can we use this analytical solution? Now, if we think back to our CFD code, then in a CFD code, we know the velocity at the cell centroid. This is UP, which you can see in the diagram there on the right. And we also know the height of our cell centroid from the wall, YP. Now, if we compare that flow scenario in our CFD code with our analytical solution there in equation 6, we could compare the quantities and see quite straightforwardly that the wall kinematic viscosity, nu sub W, in a laminar flow situation is going to be the same as the kinematic viscosity, the material property of the fluid. And at the moment that might seem quite straightforward, but as we extend this to consider turbulent flows and locally laminar flows, it's very important for us to remember this key result. So for a laminar flow, what we would do is we know the velocity at the cell centroids in all of our wall adjacent cells, and we know the distance to the wall, and then we multiply that by the kinematic viscosity of the fluid, and that'll get us the wall shear stress. Now, at this point, it's also very important to point out that our wall kinematic viscosity, nu sub W, does not depend on the value of y plus. And that's because we've just used a straightforward assignment there that it's going to be the same as the kinematic viscosity of the fluid. And this is a very important result because it's telling us that y plus does not affect the calculation of the wall shear stress when we have a globally laminar flow. So when you set up and solve your globally laminar flow simulation, then the wall shear stress is going to be computed using the same formulation regardless of what your y plus is. Now, what this might imply is that we don't have to be as strict with our wall resolution when we're meshing our geometry as we might need to be for a turbulent simulation, where we might be restricted in our value of y plus to, say, less than 5 if we wanted to use viscous sublayer resolution. That restriction doesn't apply to a globally laminar flow situation. Of course, it's important to remember that the opposite is true, and we shouldn't take this as an excuse to make our cells as large as we want. And of course, the reason for that is that we still need to capture the gradients and the profiles throughout the remainder of the flow. And just as a simple example of this, you can see in the diagram the parabolic profile that you'll get for a laminar pipe flow. And if we were to use only a handful of cells across the thickness of this pipe flow, we can quite clearly see in the right hand diagram that we're not capturing the shape of the profile correctly. So even though the treatment of the wall will not depend on y plus, for a globally laminar flow situation, we still need to make sure that we have a sufficient number of cells to resolve the key flow details that we're interested in. And at this point, I'd like to make a small side point to help you in the understanding of the slides that I'm going to be talking about next, and that is the value of the wall kinematic viscosity is the value that's taken on the cell face that's in contact with the wall. And if we think of the diagram here that I produced just for a single cell, what this distinction means is that we're not taking the value of the kinematic viscosity at the cell centroid, we're taking the value at the cell face. And that's a very important distinction. And the reason for that is we may have our boundary cell with multiple faces attached to walls. And for the example there, you can see for this corner cell, then our corner cell has 2 boundary faces, and on each of those faces, of course, we may have a different wall shear stress, and we may have a different velocity profile. So that means that we need to take the value of the wall kinematic viscosity on the cell faces rather than the cell centroids. And that's going to come up a bit later. And if you've seen my previous videos on wall treatment, you may be used to this concept by now, that we're always thinking of the faces and not the cell centroids when we're considering wall treatment. So what about a globally turbulent flow rather than a globally laminar flow? And in this situation, we're solving additional transport equations for K, epsilon, omega, or other turbulent quantities. And theoretically, we remember that for a globally turbulent flow, as you see in the diagram there, the velocity profile at the wall is much steeper than it would be for a laminar flow. So what this means in practice is that if we were to use the same treatment that we used previously for a globally laminar flow, then we'd calculate an incorrect wall shear stress, which would mean ultimately that the forces on our wall and our bodies in our flow would be incorrect. So we need a slightly different treatment for a globally turbulent flow. And there are generally 2 ways we can do this to ensure that we get the correct wall shear stress in a turbulent flow. The first approach is to refine our mesh. So rather than using the same mesh that we would have done for a laminar flow, we refine and make our cells adjacent to the wall much smaller, so that those cells now reside actually in the thin laminar sublayer that's close to the wall. And in that case, if our cell is in the viscous sublayer, the flow is locally laminar, and we can use the same treatment that we used for the laminar flow that we introduced earlier. And in practice, this means resolving the mesh so that our y plus is less than 5. Now, the other approach that we can use in a turbulent flow is to artificially increase that wall kinematic viscosity, nu sub w, so that the product of the near wall kinematic viscosity and the velocity gradient, which is now incorrect, will still give the correct wall shear stress. And these 2 different approaches are often called the viscous sublayer or wall resolved approach, and the log law approaches. You may see them referred to in other videos and other sources on the internet. So how does the CFD code work, and how does it cope with these turbulent flow situations? The first step to remember is that for all simulations, the CFD code will always calculate y plus. So it doesn't matter if our flow is globally laminar, turbulent, or locally laminar, y plus will always be calculated by our CFD code. And of course, you can visualize y plus and look at it and see what values you have in whatever post processor you're using for your CFD code. If that's ParaView, FieldView, CFX Post, TechPlot, or whatever post processor you choose, you can always view and look at y plus, regardless if you have a laminar or a turbulent flow situation. However, of course, as we showed before, the value of y plus that's calculated just won't affect the calculation of the near wall kinematic viscosity if the flow is globally laminar. But what if the flow is turbulent? So if the flow is globally turbulent, we use equation 13 there to specify the wall kinematic viscosity on each of the boundary faces. And the way we do that is that if the y plus value is less than 11.25, then we assume that the flow is going to take the viscous sublayer solution, and we assign the near wall kinematic viscosity with the kinematic viscosity of the fluid. Now, if the value of y plus is greater than 11.25, you can see there that what we have to do is artificially increase the value of the near wall kinematic viscosity there, so that the product of the near wall kinematic viscosity and the velocity gradient will give us the correct wall shear stress. Now, if you've seen my previous videos, you'll note that this value of 11.25 is to ensure that we have a smooth transition and that we have an assigned value of the near wall kinematic viscosity in the domain over the entire range of y plus, so that it doesn't matter what our y plus is. And of course, if we wanted to get an accurate solution, we would need to ensure really that our y plus is less than 5 if we wanted to use the viscous sublayer solution, or greater than 30 if we wanted to use that modified formulation. And if you're unsure about where this comes from or need a reminder, I would advise you to just go back and have a look at my previous videos on wall functions and the difference between y plus and y star, and this transition region is explained in a lot more detail. But for this video, what we then move on to do is use equation 14 for the wall shear stress, and it's important to note here that the same equation for the wall shear stress is used for all simulations, regardless if the flow is globally laminar, globally turbulent, or locally laminar. It's given by the product of that near wall kinematic viscosity and the linear velocity gradient there. Of course, if our cell is in the log law or turbulent regions, we're going to be using a modified value of that near wall kinematic viscosity to ensure that the product and the overall wall shear stress is correct. So hopefully for you in this slide, I've really spelled out for you very clearly exactly the different treatments that the CFD code will use. Now what I'd like to do is move on to talk about what happens if the flow is locally laminar. And a locally laminar flow is likely to occur if we have a multi-phase flow or the flow of a non-Newtonian fluid. And what happens in these simulations is that the kinematic viscosity nu, which is a material property of the fluid, actually varies throughout the domain. And far from the wall, we might find that the value of the near wall kinematic viscosity takes the value of, say, water or air, but close to the wall, where we have a build-up of non-Newtonian fluid, then the material property, the kinematic viscosity of the fluid, may be much larger, and the flow could be locally laminar near the wall. And one such example of this might be if we have a flow of sludge and water in a pipe, for example, as you can see there in the diagram. Then in the free stream in the water, where the flow is predominantly water, the flow is likely to be highly turbulent, and the kinematic viscosity takes the kinematic viscosity of water. But close to the wall, where we've got a thick sludgy layer, the kinematic viscosity will be much larger, and we expect our flow to be locally laminar. So how does a CFD code account for flow scenarios like this? Well, the first thing to note when we set up these simulations is that the turbulence equations will be solved throughout the entire domain, and that will mean solving equations for K, epsilon and omega. And as a result of this, the CFD code will calculate the value of the near wall kinematic viscosity, the kinematic viscosity of the fluid, the material property nu, and the turbulent kinematic viscosity nu t will be calculated throughout the entire domain. So every cell in the domain, regardless of whether it's in that turbulent free stream or in that laminar sublayer, will have a kinematic viscosity and a turbulent kinematic viscosity. And as before, these values are calculated at the cell centroid, which you can see there in the diagram. But as we saw before, for the wall treatment, we need to know the value of the near wall kinematic viscosity on the cell face that's in contact with the wall. So how does the CFD code account for this? Well, the values on the cell faces are calculated using central differencing. Now, if you've seen my previous videos on upwind and central differencing, you'll remember that central differencing is basically the same way as saying linear interpolation or linear extrapolation. So the values of nu and nu t on the cell faces are calculated by extrapolating from the cell centroid values, and then using the value of nu, that's the kinematic viscosity, the material property of the fluid on the cell face, we use that to calculate the near wall kinematic viscosity nu w, which is then used to calculate the wall shear stress. So what this means is that the turbulent kinematic viscosity nu t, while it's calculated at the cell centroid and the cell faces, doesn't enter into the calculation of the wall shear stress at all. And it's very important to remember that. So how does the CFD code distinguish between a locally laminar flow or a locally turbulent flow? Now, in that previous example that we saw where we had water with a thick layer of some type of sludge near the wall, then that will result in the value of nu, or the material property of the fluid, being very large near the wall, because the flow is very viscous near the wall. And if the flow has a very high value of kinematic viscosity near the wall, that necessarily means that the value of y plus will be very small. So if you look at equation 17 there, if the denominator on the bottom is very large, that means y plus will be very small. And so if y plus is locally very small, then the CFD code will automatically use the solution for the viscous sublayer, which you can see there in equation 18. Because the value of y plus is small, then the near wall kinematic viscosity there will be taken as the value of the laminar kinematic viscosity locally at that wall position. So what that means is that actually the CFD code is very clever, and it will take the laminar treatment at the wall when and where is necessary. So we'll use the same setup as we would for a globally turbulent flow, and the CFD code will automatically take the laminar value where the flow is locally laminar. So just to wrap up with a quick summary of what I've talked about today, hopefully this may have cleared up any confusions you have. For all flows, the CFD code will calculate y plus, and you can look at this value of y plus in your chosen post-processor. Now, if the simulation is globally laminar, that means we haven't enabled any turbulence equations at all, then the value of y plus doesn't affect the calculation of wall shear stress at all, doesn't even enter to the process. But of course that means that we can't just make our cells as large as we want, we still have to have sufficient cells in the domain to capture the profiles. Now for a multi-phase or non-Newtonian flow, for example, the flow near the wall may be locally laminar. That means locally it has a very high viscosity value. And for these locally laminar situations, the CFD code is very clever, and it will automatically choose the value of the viscous sublayer solution, the locally laminar solution, because the value of y plus will be very small anyway. And what this means really, if you think about it in detail, is effectively for those locally laminar solutions, we're effectively saying that we have a very thick viscous sublayer in our CFD solutions. So CFD code is very clever and will help you out. You won't need to do any additional messing around to get that to work. And I'd just like to wrap up this talk, as always, by thanking all of you for your continued support with my videos. I really do appreciate all of the comments, feedback and suggestions you leave in the comment section. It really does help me. And in particular, I'd like to thank my patrons over on Patreon for supporting the channel even further. And if there's a way that you would like to get involved a bit more and help support the channel, there are a number of ways you can do this. You could either say buy me a coffee or leave a donation on PayPal. There are links for those in the description below. Or you could follow along on Patreon and become a patron of my channel as well. And one benefit you get for doing that is I upload to Patreon PDF lecture slides of all of the lectures that I've delivered here on YouTube. So if you'd like to get access to those and view them in your own time on whatever device you have, or maybe print them off, just head on over to Patreon and you can get a copy of the slides there. And as always, I'd just like to wrap things up by thanking you all again. And if there are any suggestions you have for videos you'd like to see, or perhaps you've noticed some things in my slide that aren't quite clear or need a bit more explanation, or maybe I even made some mistakes here or there, please just leave them in the description below, and inevitably I'll get to those as quickly as I can. And thank you all very much for watching, and I'll see you next time.